Welcome to Reliability Matters, a podcast for the electronic assembly industry. Each episode covers topics related to reliability, best practices, and environmentally responsible assembly techniques, with insights from experts across the electronic assembly industry. Now, here's your host, Mike Conrad.
Dave Hillman is a metallurgical engineer in the Advanced Operations Engineering Department of Collins Aerospace in Cedar Rapids, Iowa. He serves as a consultant to manufacturing on material and processing problems. He served as a subject matter expert for the Lead-Free Manhattan Project in 2009. He's published numerous technical papers and was presented with the 2008 SMTA International Conference on Soldering and Reliability Best of Conference Award and was a recipient of the SMTA Member of Technical Distinction Award. Dave was awarded the Vinci Medal as a Rockwell Engineer of the Year. He also serves as the chairman of the IPC JSTD-002 Solderability Committee. He's also a member of the SMTA, where he serves on the SMTA Journal and Soldering and Surface Mount Technology Journal Technical Paper Review Committees. He's a member of the American Society for Metals, the Minerals, Metals, and Materials Society, and IPC. If you're in the electronics industry, you've probably seen Dave at numerous technical conferences, imparting wisdom with a unique style to Dave. Here's my conversation with Dave Hillman. Dave Hillman, it's so nice to see you today.
Hi, Mike. Glad to be here. Looking forward to having a fun discussion today.
Yeah, the only thing that can make it better is if we were having it over a couple of beers in a bar, but that's not the case. So this is the next best thing.
Exactly. We'll do it in 2021 somewhere.
Yes, we will. I think all of us are ready to party in 2021, even with people we don't know. You know, just pick people off the street and invite them home. It'll be a welcome experience again. So if 2020 were a year, I've seen these memes lately. If 2020 were a year, it would be this, and it shows a roll of toilet paper, only someone photoshopped it into a cheese grater, right?
It would be.
Or a pie filled with gross things, So if 2020 were a year, it would be this. So I think if 2020 were a component, it would be a bottom terminated component. That's the way 2020 is. That's the way I feel about BTCs in many regards.
I would think of a MELF because I my QFNs, my bottom terminated components I can deal with. MELFs, round part on a flat board just seems like a silly thing, but
right.
But yeah, the industry's, it has been an interesting reaction, when the bottom terminateds first came, all us old timers looked at it and said, oh my goodness, the ceramic LCC has come back. Now what are we going to do? And, it's quite a different story when you start looking at the materials, but that initial reaction kind of brings everybody back to, oh my goodness, BGAs. I can't see the solder joint. How are we going to do anything right?
That used to be the big concern, right? No one understood how, and that's what brought in pretty much X-ray into our industry. I mean,
Exactly.
X-ray's been around for more than 100 years, but it's been used mostly for, dental and medical and other types of inspection things. And then I think, my theory on voiding is X-ray causes voiding. Because before X-ray, we had no voiding, right?
So when the electrons leave the material, they're actually leaving holes. Okay.
They are.
That one
They
I'll
are.
have to take back to my profs and see what they think about that.
Yeah, they didn't teach you that in school, Dave? Come on. What school did you go to?
Well, yeah, and there's a lot of parallels there. When BGAs came, we couldn't see the joint. We had to suddenly rely on all this process control we wanted. Cleaning, oh my goodness, now we got to clean under there, and you've been through those wars. So there's a lot of parallels to bottom terminated versus the BGAs, and we survive BGAs. We use them now. People like them. They're highly popular, and our boards are quite dense with them. So, I have confidence we'll make it through the bottom terminated introduction as well, or its evolution.
Sure. It is interesting the way this industry works, and probably every industry has this phenomenon where a new technology is introduced without any instruction set on how to actually implement it, right?
We don't get training wheels. Here you go.
Right.
If someone said Mother Nature's a cruel teacher, you get the test and then you get the lesson. So
exactly.
We've done that with BTCs. We've done that with BGAs.
That's right. I have a theory, and for my audience who's come to my webinars and things like that, they're going to roll their eyes because it's like an old dad joke, told repeatedly. But I have a theory about, children. When you raise children, you need to reinforce how much you love them. And for those unfortunate children who grew up without that reinforcement, one of two things happened. They either became sociopaths and serial killers, or they became designers of bottom-terminated components.
I could believe either one of those very well.
They got back at society. So voiding, of course, is kind of the general topic of today. We can stray into any other direction, any other vice or problem or issues that we're having in our industry. But I was talking to a group of people the other day about voiding, because in 2020 there's nothing else to do, and I've asked several of my guests this question, and I've received answers back, and I'm going to ask you the same question. Is voiding overrated? And IPC has the BGA voiding spec of 30%, cumulative. I don't know if that number came from a tarot card or a fortune cookie or science or
came from Rockwell Collins data.
It did. Yeah, oh my gosh!
That. Absolutely, I know that history. My therapist said not to talk about it, but we'll talk about it anyway.
Well, I'm so glad I asked you that question, because the answer that generally I get back is, yeah, it's overrated. It's it's pie in the sky. It's rather random. So I am actually, which wouldn't surprise me, by the way, but I'm in the cleaning business, and we had a cleaning spec that was kind of chosen out of thin air, 35 years ago, right? You know which one I'm talking about, which is now gone, thankfully. But I was curious if the same phenomenon, resulted in a voiding standard, or if that actually was based on science. And if it was based on science, what criteria? This is kind of, I tend to ask questions that morph into several questions, all within one question.
We just got to remember to come back to the other side.
I know, right? Right. Yeah, it's a trail of breadcrumbs, which will lead me to what types of technology or what types of environmental in-use applications, or what type of reliability expectations, et cetera, would determine if a certain percentage of voiding is too high or too low. So there we go. It's a compound question. We'll
start with parts and bounce around to the various regions. But yeah, and everything, we're going to end up talking about bottom terminated, but it really does have its roots in BGAs. One of my mentors told me that we as engineers should all have paid attention in sociology class, because engineering is easy, people are hard. And what has happened is that we've got this brand new technology called ball grid arrays. And when we got that, we said, well, we've got to see the solder joints. Well, what's the easiest way to see a solder joint? Well, we'll cross-section it. Well, okay, that's great, but I can't sell the product when you're done with it, Dave. So let's go to X-ray, because, X-ray in the medical world and X-ray in the dental world, and we've done X-rays. We kind of know how to deal with that. And so we X-rayed them, and lo and behold, what did we see? We saw voids. And the first thing, human reaction to something different is it's bad. No, it's different. So when we see voids, we don't know it's good. We don't know it's bad. We as an industry have to go determine that through data. And it was quite interesting when we introduced BGA criteria to the J Standard 001 national standard. It was set at 10% was in the committee. We're talking about 10%. And Les Himes had looked at that and said, well, that's awful low. And there were a number of people who Mike said, just like you said, hey, wait a second, voids don't really mean anything, especially a couple friends at Motorola. When Motorola was king with the cell phones, they had looked at it extensively, just hadn't published the data. And so Rockwell Collins and Lockheed Martin and Northrop Grumman and you name it, a ton of companies got together and looked at the available data and said 25%. And that's what went in. And then about 6 years ago, Rockwell Collins took a look at it, and especially, as you said, there were a number of people in the industry, hey, this is ridiculous. 25 is low. And so we did our test, and I'll remember that test quite well, because I took 40 circuit boards and I ran them down our process, and which ends up being about 250,000 BGA solder joints. And guess how many solder joints or voids in those solder joints greater than 25% did I produce? right there. I counted them on both hands. That was it.
Both
10.
hands, that's it. 10.
We x-rayed
Wow.
every board, every part, and 10. And I'm thinking, okay, statistically, I have a problem. And I could dealt with that. We did another set of boards, and we teamed up with a couple people. And it turns out if you want to make voids, the solder paste suppliers know how. And they will give you a paste that is horrible and will produce tons of voids. My bigger problem was going back to my boss and saying, hi, I have 40 test vehicles that I can't use. Can I buy another 40? I promised to use the first 40 for something else, which we did. But yeah, it is hard to produce voids in BGA solder joints. And we did the second round when we showed that you can have a void that's almost 50% of the diameter of the BGA solder ball sphere itself. And if it's going to fail, it's going to fail, regardless of that void. There's been this long discussion, well, a void will blunt the crack growth, or no, the void causes the crack to grow faster. And in the end, it comes down to just good old global CT mismatch. If I can take a perfectly solid, no void BGA solder joint and fail it because it's in the wrong place, in the wrong design, in the wrong stress. So we went through the data again, Collins, Lockheed, HP, 10 or 15 companies got together, reviewed the data we had produced. We did a couple other tests, and in the end, 30% went in. And it's 30% of the X-ray image area. And if you go do algebra, which my co-op did and actually saved a very embarrassing math mistake in a published paper, that ends up being, if it's 30% of the X-ray image area, that's 57% of the diameter. And so, whether you're looking at it and thinking geometry or just thinking X-ray, very robust. And kind of like plated through hole fill, which is probably something else we'll talk about today. If you're at that level, something's wrong. Something is seriously wrong. Our normal ball grid array voiding percentage today in our Coralville facility is 2 to 3%. We've teamed up with our solder paste manufacturer. We've refined the profiles, and the solder paste suppliers produce some great materials. You just got to use their materials. They understand what causes voids for most of it, and they know how to work that. So what happens when we get to QFNs? We X-ray them, and in that thermal pad, which you'll hear me call the belly pad, and the IO pads I call the fence, because to me, and you know this better than I do, trying to get cleaning solution past that fence to get in that other area is to me, I think it's impossible. I don't know how you do it. It's amazing what the cleaning chemistry is designed and the equipment designed, how we even come close to doing that. The same thing, we looked at the belly pad. Oh, there's voids there. Oh, these are bad. And there's a twist to that. So when ball grid arrays, the voids, the only thing that void really related to was the solder joint integrity. QFNs came into being for two reasons. One, I want electrical functionality. I can push signal grounding through that belly pad. I can dump heat through that belly pad. It isn't just how good is the solder joint. There's functional needs. And that's where we got all wrapped up. That's why the industry has been, you don't hear the industry talk about BGA voids anymore. We don't. 30%, everyone hits it. But boy, the discussion in the committees about QFN or BTC voiding, that's been the latest craze. In this recent revision in the national standard, we finally separated it. If you need a certain percentage of solder coverage on the belly pad, that's a design attribute. And I should do that up front. I, as the assembler, I can't help you at that point. You just got to tell me what you need and whether I get it or not. And we did the work last year. It was published last year. You can have up to 50%, and the automotive industry actually believes greater, but our data only supported up to 50% voiding, and you won't affect the solder joint integrity of that part at all. So now we're going to see the industry kind of work that way. Is it greater? Can it be 30% coverage and 70% non-wetting? And I think more importantly, we've separated functionality from solder joint integrity. Two topics need tackled two different ways.
So it's interesting the amount of, at least the industry the experts are leaning toward a higher percentage of voiding, allowable voiding for that belly pad, as you call it, compared to BTCs. Did that But there's not a standard on that yet, right? That's still in like committee in the talking stages. I know there's the 30% standard for BGAs. Is there a published standard or understanding at least?
Yeah,
for,
with
BGCs?
Rev H of the national standard, it is either you do it by AA bus, agreement between vendor and user. It was put into the Chapter 7 for BTCs for the belly pad. 50% minimum is a process indicator. Now, what will happen is that 50%, instead of being a process indicator, it'll just turn into a default standard for the short term. The automotive folks, talking with our friends at Continental and Bosch, they are producing data that will probably, the next rev of the specification could take it from I need 50% wetting to 30% wetting. That's just our data. That's all the farther I could get the process to go. Kind of like BGAs. If I wanted to make bigger voids, I was having trouble doing it. And so, hitting 50% minimum should not be an issue for anybody. If a good, well-designed, in-control process teamed up with a solder paste supplier who's giving you good materials, teamed up with your stencil manufacturer, hitting 50% minimum, I hope this goes the same way that BGAs did. I hope that we stop talking about that and go on to more important topics for our industry. Yeah,
I agree. Let me ask you on, I agree, and then we're going to keep talking about it. Well, when whatever percentage was agreed upon, was that only a concern about the intermetallic bond strength, the solder integrity? Did it take into account thermal dissipation?
No. So the work that we presented to committee last year and was accepted was strictly and only solder joint integrity. What keeps it part on the board? And we cycled minus 55 to plus 125, which is the avionics. I come out of producing things for airplanes, so you're literally fall back to the avionics world rather than the handhelds or space or one of our other market segments. But that's minus 55 to 125 is a pretty big range. We went 3,000 thermal cycles. We kept the stuff in the chamber. In fact, we broke the chamber. It took a year and a half and the chamber broke. We said, okay, we're done because I need to pull it all out of the chamber. 3,000 thermal cycles. If you look at the Weibel distributions and the N63 and the Weibel characteristics, the solder joints have N63 values north of 1,000 cycles, which is well above what most people need in their designs. So our quest, our objective of that test, what do you need for the solder joint? Because I have my design teams telling me, I need a certain amount for thermal dissipation or for grounding. So if you need that functionality, and that's where the standard was very comfortable, that's a design attribute. You do that up front as part of your planning. When I send my board to Hillman's contract shop and he's soldering them, I don't know what the design attributes of the part is. I just know what the solder is supposed to be. So if it's something better than 50% for solder joint integrity, put it on the drawing. Tell me this part is special and I need to do something different. And we can do that. We see that all the time on drawings. This part needs a certain amount of wetting or needs certain fillets, or you need to do this because it's necessary for the part, not exactly necessary for its integrity.
Right. So you talked about cleaning a little earlier. One of the challenges we face in the cleaning industry is, of course, getting under these fine pitch components, and
good luck with that.
Well, it's an ongoing battle as the component continues to drop, closer to the board. But we managed to do it to acceptable levels between the marvels of chemical and then in the wash process, which they cheat because they can lower the surface tension. They can make skinnier water. The rinse process is where the equipment has to earn its stripes because we can't add a chemical to lower the surface tension in the rinse. Because
you're trying to rinse.
We're trying to rinse, right? So that's just sure mechanical brute strength and water particle size and impact pressures, all those tricks of the trade. But one of in the world of no clean, and I'll overly simple make this simple for my own edification, my own good. No clean works primarily by during the reflow process burning out all the bad actors, the activators and things like that, and then encapsulating some of those bad actors. In a resin-rosin layer, which itself is benign, non-conductive, and it's basically little resin jails for all the bad actors that are conductive, corrosive, right? So when the thermal peak temperatures and the profile are performed properly to the solder paste specification, everything is cool. All the bad actors kind of disappear. The flux residues are largely invisible and pretty benign. And the world is good, right? The sun rises again the next day. On my experience tells me that the same phenomenon that causes voiding, which could cause, depending on the amount of voiding, solderability issues, the integrity issues, it could cause heat dissipation issues. What a lot of people don't draw the line to, there's a third issue, and that is what's causing those voids in many cases is entrapped gases, fluxes, and they can't outgas, they can't escape, so they kind of push the solder around and prevent it from wetting to that particular area. And what's left after reflow is quite frequently unactivated flux activators under the component, which can be problematic.
Those gases are supposed to leave.
They're supposed to go away.
They're supposed to stay under there and camp out.
Right. It's like a house guest at Thanksgiving that won't leave by Christmas. It's just, they're still here. So that's quite problematic. Now, it's not problematic if you're running a flux that you're intending on cleaning, because then all you have is the challenge of getting under the component. But if
just that.
That's all. That's it. Yes. Day in a park for us. But
I tell you, I'm more scared about BTCs because BGAs. What you and your colleagues in the cleaning world for our industry do is just chemistry is amazing. Metallurgy is easy. Chemistry is this black art. I don't know how you guys do it some days. But with BGAs, the largest BGA we have in the factory right now is 2,600 IO. It is almost 3 inches square.
Wow.
I don't know how anybody gets anything, and we've pulled them off and looked at them. And the reality is no matter how well you clean, there's always a little bit of residue. And so it kind of goes back to what you said. It's this partnership of your process, the material you're using, and what you're going to do. I'm always going to leave a little residue someplace, and that residue better be fine. And with BGAs, I wasn't too worried. Right around the pad, it's not bridging anything. When we looked at QFNs, and Dave Adams, and Dave, was our cleaning guru before he retired. He came and I soldered our first test boards down, and he looked at him and said, that's a 3 mil gap. And I said, is that a problem? And he said, yeah, this might be. And so we spent considerable time. How do you get a fluid under a 3 mil gap? And then I have this fence, and it isn't these isolated spheres in a nice array that I can, do solution from an X or a Y direction. I am more worried. I've never been worried about the solder joint integrity once we did the initial test. It's the cleaning. And you're right, because we clean if we do a half bad job. I was going to say half-ass, and I'm still going to say half-ass job of cleaning.
That's an IPC term. I
you
think.
Proved it's bad.
We're all on the half-ass committee. Yeah.
And so I would be, in many, many cases, both you and your colleagues have proven, leave it alone. Trust your chemistry. When we start to fiddle, and so, I think we've asked you to do the impossible job. I want a material that I want to clean out of there. Why not I just leave it alone? And so, that's my bigger, you bring up the bigger voids. Who cares about voids? It's cleaning under there for the environment I'm supposed to be in.
Right. And the point I was making is the voids, I agree. Who cares about the voids? You guys have done your work to know what's acceptable, what's not acceptable. And if anyone can do that right, it's Rockwell Collins. But what the problem is the more voiding, the more residue that's under there. So you could, if your plan was to run no clean and not clean it, which is probably not real common in the avionics world and military and space and all that, and medical, they tend to clean things. But if you're running a commercial application that for no other reason needs to be cleaned, and you have voiding and you're running no clean, I can guarantee you need to clean that. Even though you're running no clean, because we did not give the no clean a chance to completely outgas the activators and encapsulate them. So No clean is no longer a no clean if there's voiding below a BGA or below a BTC. And when going back to your fence analogy on BGAs, I liken it to bowling. So, anyone who's gone to a 10-pin bowling alley will know, there's 10 pins there, and a bowling ball can, if you get it just right, you can knock down all 10 pins. Now imagine if they came up with like a super bowling that had 100 pins, right?
Oh, this is going to get no thank you.
There's no angle that will get all 100 pins knocked down. And that's what these 3-inch BGAs are. They're a bowling alley with 100 pins and a smaller bowling ball, then
I give you a bottom terminate. Not only do I give you one fence, let's put 2 rows. Let's put 2 fences under there and let's offset them.
Yes.
It is a great component. It is QF bottom terminated parts. I say QFN quite a bit because that's just the slang term for them these days. But BTCs are great. They are highly reliable. The design community has lots of functions, but when you look at them, it is probably the hardest cleaning challenge we have ever had. It's the hardest printing challenge. We're really good at single fences. I can deal with 2 fences as long as it's 0.5 millimeter pitched, a few 0.4. We don't process 3 fence QFNs. I can't print it. I have yet to figure out, and there are some people in the industry that have, how do you print paste on the belly pad and then get paste on 3 rows of fences, and they all have the right buoyancy that nobody dances the wrong way in bridges. Right. I gave up. We can't do it. And so we do 2 rows and 3 row, or 1 row and 2 row, and we just don't allow 3 row. And luckily there's not a lot of demand for the functionality of what a 3 row does. And I just look at 3 row and said, okay, no clean, because I'll never clean it. I'll never get in there. I don't know how you get under single row, let alone 2 fences.
Right. From a printing standpoint, is that 3-row challenge, a stencil challenge? Would that be something jetting could overcome?
Yeah, and a lot of people that
forget about
jetting.
The throughput.
Yeah, absolutely. And you're seeing QFNs, and along with now come along the 0201s, or as our good friend Doug Pauls will say, the 010 halves, because we're not going to say 005. So the 010 halves are. I kind of believe with 0201s, you sprinkle them on the board, you solder it, and then you shake it, and whatever falls off, those are the ones that didn't solder. I don't even know how you see these things. I know that someone said, how are we going to clean them? And I said, well, the good news is you're not putting down a lot of paste with a residue that needs cleaned off. So be thankful for that. But yeah, the boards tend to be higher complexity, smaller size. So you're lucky you can use a 3 mil stencil or a 4 mil stencil with a nice coating, a slick coating that allows better release. But yeah, you're fighting, that center pad is a large solder volume and the fences are smaller solder volumes. And you're just playing with that buoyancy of, okay, what's going to float it around? And to make your job even worse, remember when BTCs all had uniform pads and spacing? Let's just mess them around where now the uniformity is gone. I mean, they'll have big pads, little pads, all danced. There's no clear, clean. I like your bowling alley. I can't throw a bowling ball down underneath the BTC anymore because I keep hitting all sorts of pads.
Sure. So again, parents, reinforce the love for your children every chance you get, or they're going to come up with worse components. One of the challenges in cleaning is, we direct fluid out of a nozzle and it heads toward the target. Once it ricochets off that target, it loses about 80% of its energy.
Oh, wow.
So, imagine a water cannon in a riot. It's not hard. It's not too hard to imagine these days.
Seen a few of those this year.
Yes, exactly. So the water cannon hits protester 1 and knocks that protester back 12 feet. Water from that protester splashes off the protester, hits the person next to them, and they just get wet. They're not knocked down. Once water ricochets, it loses the majority of its energy. Now, apply that to BGAs. So fluid has to enter the first set of obstacles, and that it's hitting with 1 degree of separation, or 0 degree of separation. Then it bounces off and hits the one behind it, 2nd degree of separation, and next thing you know, you have 20 degrees of separation, and the parts are barely perspiring, much less getting high impact fluids. So that is not so much part of it lies on the cleaning machine, but that is the ability to clean multiple row BGAs is a testament to the chemical companies, because for particularly aqueous processes to work, not talking solvents now, because solvents are rarely used in production anymore. It's mostly aqueous. The interaction between the wash solution, which is water and chemical, and the target has to have an exchange of energy, not just contact. Solvent was contact. Just dunk it and it'll dissolve. We're not dissolving things anymore. We're bringing things into solution through the exchange of contact, heat, time, energy. And the amount of energy is really important to force that either saponification process or solubilization process to take effect. And as we lose that energy every time, like a pinball machine, every time the water bounces off another ball to another ball to another ball, that puts the responsibility on still having enough energy to clean the part on the chemical company. They now have to clean with less energy than they used to, because we're not cleaning a one-dimensional part anymore. This is the matrix of components here. So it does put a lot of pressure on the chemical companies to be able to force that solubilization process or saponification process to take effect with less and less energy compared to older chemicals, which we didn't have to worry about those obstacle courses at the time.
Well, and think of a BTC as a BGA on steroids, and we started out where they were 6x6 and 4x4 and 5x5 millimeters. They're fairly small, and we were able to, cleaning was pretty well. Well, now if it's really good, let's make them bigger. So I'm starting to see a trend from our design teams of 10x10, 12x12. QFNs, BTCs are getting bigger, and which means all those troubles are just going to get magnified. I got to believe the limiting technology for BTCs won't be the soldering. I think I can always solder them. What do I do in the cleaning? How do I deal with the residues? What are my corrosion concerns for that product use environment? That's the bad part. I've got a feeling there will be, like any part, you can find the wrong environment with the wrong process, and the board will corrode. No matter what we do, we can't stop it. And that's where the conformal coating materials, the paralenes in the world, come in and try to save us. But if BTCs start this trend of 10x10 millimeter, 12x12, 14x14, I think there's a limit. I think we're going to find a limit where if you are not doing no clean, you maybe need to think, like you said, go to jetting. Let's do something very precision with the amount of paste, rather than stencils are great technology, but it puts down large blocks of material. Maybe we need to tailor that. And I think maybe that's why you see the jetting equipment, not just for the O201s, but other technologies. We found where, hey, having that precision, that's a cool thing. Maybe we can use that to our advantage in other cases, other situations, other part technologies.
Yeah, very good. It seems to me the mitigation to voiding is to, basically raise the bridge or lower the water. One of the two, or both. Right?
As a kayaker, I like the bridge going up. It makes me a lot more happy, because I know what happens if the water goes up and the bridge stays put.
That's right. Then you
get scraped out of your boat, and it's not pleasant.
No, I can imagine that. So I've heard and allowing outgassing channels, window painting, things like that. So there are a lot of mechanical tricks, building dams, bringing the mask down, or expanding opening up the mask area, or raising the mask area to get more clearance underneath. All of these are mechanical tricks. Do those, in your experience, do those techniques have merit? Are there other techniques that are being worked on that are publishable that would also mitigate the voiding concerns?
That's actually a really good thing to bring up. Number one, first and foremost, it's your paste. We learned that in BGAs. We're seeing that in BTCs. Your solder paste, its composition, its chemistry, that determines voiding. the reflow profile plays a role, and there's other things playing, the surface finish, gold, is it tin, is it immersion silver? But first and foremost, the top of the Pareto chart, I've got to have a paste that's low voiding, it's great characteristics. But then it bounces into something interesting, and that's that design. And put a plug in for the IPC 7095 committee. That is the, 7093 committee. That is the BTC design guidelines. And Matt Kelly and Udo Weitz from, Matt's now with IPC and Udo's from, oh heavens, one of the automotive guys. They came in, and that specification is out now. Tremendous amount of revision, and exactly at the item you talked about. How do I print paste? What patterns do I print paste? What do I do with the microvias, and how do they interact with creation or aiding making voids or stopping voids? What do you do with the different solder mask areas? There's one they call striping. I call it zebra striping, where instead of doing blocks of mask, just think of the belly pad having stripes of solder mask of a certain width to allow channels for all that gas to go away. And like you said, if it's not trapped under there, it's not going to cause me a problem. So the 7093 specification has 2 whole brand new, completely revised chapters with the latest and greatest solder mask and microvia technologies to aid in what we do in getting those the voids out of there. I mean, I'm an old-time engineer. It's easy. Cap the darn vias. If you're going to put a microvia in there, just plate it shut, fill it and plate it shut. And of course, my buddies in the fabrication industry say, "Oh, you just dumped your problem on us." And I said, "Yeah, I did, because if it happens up front, I don't worry about it toward the end." But yeah, exactly. What am I doing with vias? What am I doing with solder mask? Huge advantage now with the new specification and new ideas on how to deal with that.
Yeah, excellent. Yeah, this is an industry of pass the problem. You've heard the old game of telephone that kids play.
Yes.
And ours is like here. Or maybe a better analogy is like a hot potato. You pass the hot potato, the hot component to other things, to the next group in the assembly line. So BGAs were historically the poster child of problem components, and now we wish all we had were BGAs, because BTCs are
those are easy.
QFNs and other types of components are now the poster child of troubled components. What else out there gives our industry trouble, particularly from a metallurgical point of view?
Well, I always love what my mentor said. Let's go solve all the problems we don't know yet. Wait a second, what? Yeah, and so we don't know what's coming, and some bright young man or woman will come up with some neat stuff. But I think what's probably on our short-term horizon, you mentioned earlier, X-ray. We now have a non-destructive technique that sees all kinds of stuff. So there are people that have, I go to the doctor and I get a CAT scan. I go to the dentist and I get an X-ray. Somewhere along the line, someone says, "How many REMs have you had for the year?" Because there's a certain amount of X-ray exposure, and our boards are no different. And, there's some pretty good guidelines right now. The IPC National Standard J001 has taken that first step. And how do we carefully, gradually, with thought, introduce rules and requirements around X-ray? But, I'd said it earlier. So I X-ray a board, and I see things that are different. Well, we had plated through holes longer than you and I have been in the industry. And sure enough, what do we see in those plated through holes? Voids. Are they bad? Are they good? And so the next real big push now, once we kind of get comfortable with where the BTC world is setting, is what do you do with the voids in through-hole components? Are they bad? Most of them have been there for a long time. We didn't have the analysis tools to tell us that. Are they bad? Are they good? We've used 75% for a long time. Jim Reed and Les Himes, my mentors at IPC and the committees, always stuck to, 75% is where you should go. But our boards are getting thicker. They're getting a lot more copper. It's harder to solder. If I can't change the process, I'll go question the requirement. Let's see why the requirements are. It's 75 the right number. And now we have a tool. Should we be saying, a lot of people have said for a long time, 50% is good enough for many, many products. Maybe it's good enough for more products than we think. So I think that's that next step. We're going to understand what X-ray is showing me. And is that good or is that bad? And what do we need to either adjust our standards or adjust our processes? Because I know every time we change the standard, it costs the industry money. Changing standards is done based on data. And that's why I have to laugh. There was a magazine article that said the IPC standards are getting squishier and squishier. So we applied 25% voiding to all the components on our board. And I'm thinking, that's great. I don't know if you actually needed it, and you may have cost yourself money. So the national standards changed for one reason. It's that we have data that says this is the right direction to go. And so I think that's that next step. What are you going to do about voids? What about in surface mount resistors? I never saw them. They're there. We X-ray a board, you're going like, wow, I didn't think we had that many. And each component type, like you described cleaning, the soldering is a little different. And whether it's going to void or not void is a lot to do with that component type and its configuration. So I think our next hurdle is understanding how we apply X-ray smartly, and how X-ray, where do you draw the line so we don't go too far, where we're actually, the cure is worse than the disease. We're reworking things when we shouldn't be.
Right. I spoke with one of my guests. I'm trying to remember who it was, and his basic, I don't think it was Phil Zarro actually. And his basic rule of thumb is no rework.
Yeah.
If something looks kind of sloppy, the art of rework puts the part in more jeopardy than just leaving it the way it is. Even if it's a slight solder defect, it's not coming off the board. If it doesn't quite meet the standard, it's probably more dangerous to rework it and subject the entire board to, spot cleaning or whatever, more handling than it is to just leave it the way it is. I used to fly airplanes, and there was a philosophy we called the big sky rule. And that was, if it looked like we were going to hit another plane in the sky, the best action is not to do anything, because changing your attitude, you might take up more airspace if you try and move out of the person's way, and the chances of hitting are very, very remote. It happens, but it's extremely rare. Usually, it's best to just I don't know. I don't think they ever said this, but close your eyes and take your hands off the wheel. Right, just don't increase your profile. Your space profile. So the same probably applies to a certain degree to what we're talking about.
Oh, the number of times Dave Adams has chewed on me because I reworked something. And if you thought the residue just coming out of the normal process was good, I know you've seen rework residues, and they're,
sure,
they're caramelized, they're cooked. They're
much harder.
And now I expect you to get those off for me. So yeah, right. Why even deal with the whole thing? I'm with Phil. It's just, hey, don't rework. Figure out that, hey, maybe that's okay just to leave it alone.
Yeah. Personally, from a completely selfish business standpoint, I'm for voiding, because, let the standard go to 90% voids. That's great, because the more voiding, the more likely problematic residues are going to be underneath in that void. So, I think the drive on coming up with a acceptable voiding number probably didn't take too much consideration into what's inside that void. It's
zero.
In many cases, it's not a void.
Yeah.
It's not empty. It has flux residues and activators and things like that in there. It's not necessarily dry, which is great for our industry, because
that's a hot
means
potato. Here you go. Oh, my solder joint's fat, dumb, and happy. There's these weak organic acids and copper. I don't know if that's a bad combination, but I'll leave that to you to deal with, how that goes through. Oh yeah. And we did, the research we did last year, the investigation was to solve one piece of that recipe and to say, okay, here's where you're at with its solder joint integrity. There, like anything in our industry, those equations don't have one factor. There's too many other things, like you said. How do I put vias and solder mass down to aid that versus, okay, I'm just going to completely 100% rely on my cleaning equipment and chemistry to save me. And it can't. It's too complex. It's got to be, one of the guys here called it an ecosystem. And if you look at our soldering process, it is an ecosystem. How do I control a print? What's my reflow? How do I clean? What was the design? And one of those gets out of whack, just like in our normal world around us, things start to be suboptimal.
Mm-hmm. Yes, absolutely. So you come from a metallurgical background. What other metallurgical monsters are out, threatening our boards?
Lead free. I mean, isn't that the topic of the world is lead free? I'm hoping that it goes. I'll be retired before it does go away. I know that, but it is interesting. We spent 60 years using one material. And now people say, oh, we got to go change the drawing notes and we need to put symbols on everything. And I kind of step back and say, so when you were reworking a board, you didn't look down at the drawing? Oh, what do you mean I had to pull the drawing? We've had one material set so well established that we got lazy. Right. I don't got to look at stuff. And now, so we've been doing lead-free soldering at Collins Aerospace now for about 10 years. Well-developed material set using SAC 305. But we did do one consolation, and the solder mask on the lead-free boards are blue. It goes back to human behavior again. Yeah, I could look at the drawing and I got everything set right, but when I get a blue board in front of me, I don't have to think, oh, blue, lead-free. What do I do? And all the processes fall into place. So lead-free is where we're going. We have the commercial world's done a great job. They've established the alloys, but what you're finding now is the class 3, the avionics, military, medical space. As we start to explore that space, we're wanting alloys that are better. SAC 305 in general, the industry consensus is in low stress environments, it beats tin lead. In high stress environments, it loses a tin lead. But in many of those cases, it's good enough. It won't do as well as tin lead did. But do I need something on the B-52 for the next 97 years? No. We can replace things and do other things. But parts of the industry, the automotive guys have been doing lead-free now for quite a while, and you see a drive for them. I want something better than SAC 305. And what, of course, the metallurgists are going, yeah, there's a periodic table behind me. There's all sorts of elements on that periodic table. And we're seeing the big drive that they've taken SAC 305, and they've got down to putting bismuth, antimony, and indium. Those are 3 elements that are readily available. They understand the reactions. And we are now finding those combinations through the different consortia like CALS, HD Pug, the Cave guys, just all the different folks, INEMI. They're looking at all these new alloys, and they're going, hey, these are better than 305. So and again, the parallels are crazy. What happens when they told you Freon has got to go away, Mike? Freon is gone. Montreal Protocol is here. We're not using Freon. It led to new cleaning systems. It led to new low residue. Our whole technology improved because we were forced to. And I think lead-free is going to cause that. We are going to find an alloy that was better than tin lead. And it will cause us to change. Tin lead was beautiful. It went on and off like a light switch. It went from a liquid to a solid at one temperature called eutectic.
Eutectic, yeah.
Lead-frees will never have that. We're always going to have a small pasty range. We're going to have shrinkage voids, but we can deal with it. We're engineers. Let's go solve the problem. See, I expect 10 years from now, people will just kind of, you remember when, we're going to get rid of Freon. The world is coming to an end. You thought someone was drowning puppies. Don't do this, please.
Remember the magazines back in the day? We had actually print magazines, before the internet. I think Circuits Assembly, EPMP, whatever the other ones were at the time, were publishing on their front cover 12 months to the Montreal Protocol, then 11 months to the Montreal Protocol. And it was the conventional wisdom at the time was that the U.S. and the Western nations would be third world countries when it comes to production, because only the third world countries will be able to continue production. So we'll just basically hand the key over to prosperity over to these other countries. And I mean, it was doom and gloom. I think for the younger engineers that are listening to this program, it would be analogous to tomorrow, the EPA announces that in 12 months, they're going to ban gasoline.
Yep. All going away. No more.
All going away. It would, A, create a panic. B, it would create a sense of denial. Like, it won't happen. It won't happen. Yeah. They'll bail out of it, But this was a 10-year phase out. And solvents in those days were they were so integrated into our processes. Pretty much every board was cleaned, except there's one set of boards that were never cleaned. Those were television sets. they would just leave the rosin flux, this high solids rosin flux, on the boards as a kind of a poor man's conformal coating, right?
Yep.
But outside of that type of stuff, everything was cleaned back then. So what other, this is a kind of a detour in our last few minutes to a slightly different, well, completely different topic, but it involves corrosion. It involves metallurgical stuff, reactions that I find quite fascinating, and that's creep corrosion.
Yep.
Has our industry got a handle on that? Are they understanding the relationship between environmental atmospheric stuff like sulfur and whatever in the air that certain countries are known to have, in abundance, and a reaction on a board? Have we learned our lessons on that, or is that still?
It's like everything. I think we have. I mean, I love immersion silver. I think immersion silver is a wonderful. It's flat and it's reactive. And my RF, which stands for really freaky, not radio frequency, the RF designers think that it's great and all that. But we found, hey, you can't. We went away from tin lead. Nothing solders like solder, and we started putting gold and tin and silver in environments a little ahead of maybe we should have. And there are, like anything, there are certain environments, certain materials just can't handle. They're going to react. And creep corrosion was interesting. And I always remember, because what I was taught in school, to have a battery, you need three things. I need current, I need an ionic source, I need electrolyte. And it's a three-legged stool. I break one of those legs and I won't have corrosion. And the first few things on creep corrosion was there's no electrolyte. And so, no, wait a second. Well, there is electrolyte, and it's a monolayer of moisture or water or something on the surface. Even creep corrosion follows the basic tenets of corrosion activity. But we've learned what combinations, it was real interesting. Different parts of the world, act differently. And in a couple parts of the world where they had built over the top of landfills and the landfills were emitting gases, well, it goes up into your ventilation system and goes across your factory, and no wonder things corrode. Maybe we need to treat it differently. Conformal coat, I expect maybe the next kind of things. Where are we going with conformal coat? The nano coats seem to offer some different things. So, creep corrosion we've got our hands on. I don't think we fully understand dendritic growth. As things are getting smaller, the only thing I think saving us is we went from 5 volts to 3.3 to 1.1. We're lowering down that energy needed to drive a dendrite growth. But we're going to hit some spacing where suddenly the old rules are going to have to be challenged. And that's where the younger crowd can come in. What can they do in materials, in design, changing solder mask? BGAs, we don't do solder mask defined pads. 0201s I do, because I can't get rid of the mask well enough. I have to laser ablate and open up those pads. And wow, they work. And everyone says, oh, the solder joint on 0201 is going to die. Nope. Size matters. So by going smaller, where physics didn't change. I mean, Doug Paulus has the wand of physics, and we have yet to use it. So we still got to do what we learned in school. But yeah, I expect this next generation tackle how size is impacting what we do. And we spent a lot of this telecast here talking about this low gap size in QFNs. Other things on size are going to creep in, and we're going to need young minds to go tackle that and figure out solutions for that.
Yes, and I finally see, Doug and I talked about this actually. We talked about that silver tsunami effect, where I put Doug into that category, and
I'm in that category. Oh yeah.
Well, with silver, but they're not old enough to be. You're not walking out that door any minute. But there are a lot of very experienced, very wise sages out there implanted in companies. You're one of them. For a subject matter expert. Doug is obviously one. Many companies have their subject matter experts that are the go-to, for the entire organization. And as those people leave, they may or may not, more frequently may not, be replaced with another subject matter expert who's got the same stature and experience as their predecessor. So that is, I think, problematic, and we've talked about it several times on the show. That's, I think, problematic for the industry, because then industry starts relying on vendors who have a horse in a race, to provide Well, it may be perfectly sound advice. It may be skewed. It may be one-sided, but it still could be good advice. But the act of these people leaving was really concerning for two reasons. One that I just mentioned, the knowledge drain, and the other is who's taking their place or who's coming in on the lower ranks to work up to that future level. I'm now seeing, once I started complaining about it, I actually started noticing. So I don't know if I solved the problem, or once you talk about it, once you think about buying a red car, all you see are red cars, right? So it may be that, but I am seeing a growth in young blood coming into our industry.
I agree. IPC and SMTA both have great programs. They're pushing. I had mentors. I had people that guided me. I could go ask a question. I always laughed because we had way back when, none of our current people, we had a couple VPs that said, we'll just be a design house. And you learn real fast. If you're not getting your elbows dirty, if you're not working, you're not building, you're not talking with your suppliers, you quickly become irrelevant. Your knowledge is tied to a book. And while if you could see the other parts of my office, I've got a lot of textbooks. It's the electronics age, and that stuff is there. But, just because I saw it on Google doesn't mean it's true. And there's things on Google that funny, they're skewed a few ways. And so we still need that mentorship. We still need those youngsters, those kids as they come up to have access to people, and then they in turn will pay back. And it always happens. I mean, my mentors helped me. I've made a point to pay back to the people I can, and I think our industry does that well. So I'm glad you're seeing it. I'm seeing it a little bit, maybe not as much as I'd like, but we need that next generation to come in because the problems aren't going away, and they're going to get tougher. How do we deal with environmental stuff and yet still have material sets that are robust? And so it's going to take, engineering's easy, people are hard. We'll get some of them good people in to help us out.
Yeah, I think sometimes we're both are hard, people and engineering, right? But we're our industry in mass, smart people, by nature. So I think we do find our way out of these challenging issues like BTCs and whatever the next challenging issue is going to be. And speaking of mentoring, you have been a great resource for our industry.
Thank you.
I've sat through many of your papers. One thing our industry suffers from are exciting speakers, and you and Doug Pauls both are basically you break the rules.
A little bit. Yeah.
It's really hard to get a group of 150, 200 engineers laughing at stuff. I haven't quite figured out where their sense of humor lies, but you guys have, and it's hard enough to sit through technical stuff and, go into the weeds and stuff like that. So you guys both have the unique ability, unique particularly within our industry, to make it more entertaining. Because why not throw a few really bad dad jokes in there? Like,
well, thank you. That's why I always go to your presentations, because you are very entertaining, and it's one of the things and that I guess I'd push that to your audience too, is that when I started, when mammoths roamed the earth, as Doug would say, well, many years back, I couldn't stand in front of my audience to save my soul. And so I've taken 3 presentation classes. I took everything that Collins Aerospace had. I took a Toastmasters. I took a couple things outside, and I've learned that I don't like podiums. Podiums, I have to wander. You learn your speaking style.
Yes.
The beauty is I always used to have a pen in my hand. In fact, right now I have something in my hand because I have to do something with my hands when I am talking to an audience and stuff. So you learn what you need to be comfortable. And then the other thing is know your stuff. You can tell when a speaker really understands what they did. They're passionate about it. That would be rule number 2. If you don't know your material, the hardest thing, and I saw you do this once and I was just amazed, pick up another presenter's work because they're gone and the audience, so we're not going to skip that presentation. And there was a conference, you picked it up at one of the conferences, and I don't know how you did it, but you still made it entertaining. That's hard to do. So you've got to know your material. And the last one is don't be afraid to poke fun at yourself. We're
yeah.
Our jobs are hard. Our jobs are stressful. Doug started it and I've continued it, and luckily our management's supported it. But you'll notice that at the end of every one of my presentations, there's a funny cell. When it says questions, there's some kind of weird, strange, most of the time politically correct cell there that's like, okay, let's have some fun. And so I think I'm not one on the automation. When you do automation, it's cool. And I think pictures, it's called presentation. And we're constantly telling our young engineers, you may want to put down 50 sentences on that first PowerPoint cell. Do it. But then when you're done, I want to cook down to 10 or 5. Present to me and know your material. Use good pictures. So work at it. And it's fun. I enjoy presenting. Maybe that's why people like coming to my presentations. But I think if you've got that good topic and you think this is information people can use, sell it. Describe it, get it out there. And many times I've had some papers where in the end we didn't use it because the industry found a better way. We found, even I'm wrong once in a while. We've published something like, wow, we missed the boat on that. That paper's terrible. Look at what somebody else did at IBM or somebody at Celestica. They really, when they ran their DOE, we had the wrong variables and they had the right ones. So I think it's, admit you're wrong, have fun. And push for those opportunities. It's getting hard this year when no one got to go anywhere. And so now this video exchange where I was so pleased to see the SMTA's International show when they did it virtual, it scared me. It was so good that it's like, do we really need to be going to shows? We still need to. I think I miss the human interaction. But now we have this mixture. We've proven some electronics goes a long way. And being comfortable in the camera, like you said, is a skill one needs. It's vital. You've got to have it to push the technology and push the industry.
Dave, you are a wealth of information. Thank you so much for being my guest today.
To say thank you for having me on. It's been a privilege. I steal your stuff. A lot of my Doug actually gets mad once in a while because I'm using your cleaning cells, not his. So please keep doing what you do, because a lot of us use it and we take it down to that younger crowd as our basics for learning and starting their careers and understanding what they should do. But no, it's been fun today, and hopefully the audience finds some nuggets in here that they can use to solve problems for themselves.
Good. And hopefully the next time we see each other, it's face to face with a bar in front of us and a bartender behind that bar, and we can reminisce about the times when we couldn't get out. So I'm looking forward to that.
I'm all for that. Absolutely.
Hillman, thank you so much for being my guest today. You're a wealth of information. I appreciate all the knowledge you have and your willingness to express that knowledge and impart that knowledge to my audience. Thank you so much.
You're welcome.
Well, that's another episode. Thanks for listening to the Reliability Matters podcast. Don't miss an episode. Subscribe to Reliability Matters on Apple Podcasts, Google Podcasts, Spotify, or virtually wherever you get your podcasts. A special thanks to Circuit Assembly Magazine's PCB Chat at pcbchat.com and Ascendo Reliability at reliability.fm for syndicating this show. Thanks for your questions and episode suggestions. Please keep them coming. Send comments to Mike at mikeconrad.com. That's Conrad with a K. Once again, thanks for listening, and keep doing it right.
Thanks for listening to the Reliability Matters podcast. Join us on the second and fourth Tuesday of each month for new episodes of Reliability Matters.